Depth first search algorithm. The DFS algorithm is a recursive traversal technique used to explore all the vertices of the graph or tree. It starts at a given node, usually called the root or starting vertex, and explores as far as possible along each branch before backtracking. The traversal continues until all reachable nodes have been visited. Due to its recursive behavior, DFS can be effectively implemented using a stack data structure, either explicitly, that is with code, or implicitly via a function called stack. DFS is somewhat similar to breadth first search algorithm in structure, but it differs in a way it explores nodes. DFS dives deep first while BFS explores level by level. Now let us see the steps to perform DFS traversal. First, initialize a stack with the number of vertices in the graph. Next, select any vertex as the starting point and push it onto the stack. Third, look for an unvisited adjacent vertex from the top of the stack and push it onto the stack. Fourth, repeat the process of pushing unvisited adjacent vertices until there are no more such vertices. Fifth, if no adjacent unvisited vertices are found, pop a vertex from the stack and backtrack. Sixth, continue this process until the stack becomes empty. Now let us see the applications of DFS algorithm. DFS has a wide range of real-world and computational applications. The first one is topological sorting in directed acyclic graphs. Second, finding paths between two nodes in a graph. Third, cycle detection in a directed and undirected graphs. Fourth, solving puzzles like mazes or games with one solution. Fifth, checking bipartiteness of a graph. Now let us see the DFS algorithm step by step. Step 1, set status is equal to 1. This is ready state for all nodes in the graph. Step 2, push the starting node, say A, onto the stack and set status is equal to 2. This is waiting state. Step 3, repeat steps 4 and 5 until the stack becomes empty. Step 4 is pop the top node n, process it and set status is equal to 3. This is processed state. Step 5, push all adjacent, that is neighboring nodes of n that are in ready state, that is status is equal to 1, onto the stack and set their status is equal to 2. Step 6, exit the algorithm. This is the pseudocode for the DFS algorithm. Let's understand this with an example. Let's take a directed graph with 7 vertices to demonstrate the DFS algorithm. Starting from a selected vertex, now let us see the step-by-step DFS explanation starting from H. Step 1, we begin at node H. We push H onto the stack. This is our starting point. Step 2, we pop H from the stack. It's our first visited node, so we mark H as the visited and print it. H is connected to A, which hasn't been yet visited, so we push A onto the stack. Step 3, we pop A from the stack. A becomes our next visited node. We mark it as visited and print it. A is connected to B and D. Since both are unvisited, we push them onto the stack. Push D first, then B, so that B is on top and gets visited next, as stacks are LIFO, that is last in first out. Step 4, we pop B from the stack. B is now visited and printed. B is connected to C and F, both are unvisited, so we push them. Push F first, then C. Step 5, we pop C from the stack. C is visited and printed. It has 3 neighbors, E, G and H. H is already visited, so we can push G and E. So keep E on the top. Step 6, we pop E from the stack. E is marked as visited and printed. Its neighbors are B and F. B is already visited and F is still in the stack, so we do not push anything new. Step 7, we pop G from the stack. G is visited and printed. It is connected to E and H. Both are already visited, so no action needed. Step 8, we pop F from the stack. F is visited and printed. It points back to A, which already visited, so nothing new is pushed. Step 9, we pop D from the stack. D is the last node in the stack. We mark it as a visited and print it. D is connected to F, but F is already visited. At this point, the stack is empty and all reachable nodes from the H have been visited. Final output of the DFS order is H, A, B, C, E, G, F, D. Complexity of the DFS algorithm. The time complexity of the DFS algorithm is big O of V plus E, where V represents the total number of vertices and E represents the total number of edges in the graph. This is because in the worst case, each vertex and each edge is visited exactly once. The space complexity of DFS is big O of V as it requires storage for visited nodes and the recursion stack or an explicit stack in the interactive approach, both of which depend on the number of vertices.